In this question, a scientist is investigating the reversible dissolution reaction of gallium hydroxide, GaOH3, at 20 degrees C. Remember, dissolution just means dissolving. So on the left in the reactants, we have gallium hydroxide, which is a solid. And on the right in our products, we have gallium 3 plus ions and OH minus ions, which are aqueous, meaning they're in solution. We're told that KSP, the solubility product constant for this dissolution reaction, is 3.31 times 10 to the power of negative 34. Next, we're asked to write expressions for the solubility product constant KSP for this reaction in terms of the concentration of the ions and the molar solubility of the salt S. So remember, KSP is just the same as the equilibrium constant, but it's for dissolution reactions. So we're going to follow the same steps as we would to find the equilibrium constant. Here's our equilibrium constant equation, K. We have the concentrations of our products to the power of their coefficients on the top half of the fraction. On the bottom half of the fraction, we have the concentrations of our reactants to the power of their coefficients. And we see this note, only gases and solutions are included in the equation. So let's go ahead and write our K expression. So we've got our products on the top. Firstly, we have Ga3+. It's aqueous, meaning it's a solution, so it can be included in our equilibrium constant expression. And there's a coefficient of 1, so we're just going to have that to the power of 1. But remember, to the power of 1 is just the same as the thing itself, so we don't need to include the to the power of 1 in the equation. Next, we have OH-, again aqueous, a solution, so that can be included in our equilibrium constant expression. The coefficient is 3, meaning it's going to be to the power of 3. Then we're going to divide by our reactants. We have gallium hydroxide, but it's a solid. Because it's a solid, it's not going to appear in our equilibrium constant expression. Only gases and solutions appear in our equilibrium constant expression. So we're just going to have 1 on the bottom there. And dividing by 1 is the same as the thing itself. So there it is. That's our equilibrium constant expression for this dissolution reaction, or in other words, our solubility product constant expression. So we can fill that out here. We've got gallium 3 plus concentration, and we've got the concentration of OH minus to the power of 3. Awesome. Next, we have to figure it out in terms of S, the molar solubility of the salt. So we have gallium hydroxide. That has a molar solubility of S. Gallium hydroxide forms a gallium 3 plus ion and 3 OH minus ions. So if S of gallium hydroxide dissolves, we get S of gallium 3 plus formed and 3S of OH minus formed. So putting that into our equation here, gallium 3 plus has a concentration of S, OH minus has a concentration of 3S, and it has to be cubed. So we're getting S times 3 cubed, which is 27, S cubed, which gets us 27 S to the power of 4. So we can fill that in here. Awesome. Okay, so we have an expression for KSP in terms of the molar solubility of the salt S. We're next asked to calculate the molar solubility of gallium hydroxide. Now, we were given KSP in the question, so we can use that in our equation here to figure out what S is. So let's go ahead and write that equation again. We've got KSP is equal to 27 times S to the power of 4. We need to find S, so we're going to divide by 27 on both sides. Then we've got S to the power of 4, so we're going to need to do the fourth root. So that gives us S is equal to, because the fourth root and to the power of 4 cancel. The fourth root of KSP over 27. So let's put that into our calculator. KSP is 3.31 times 10 to the power of negative 34 divided by 27. So let's put that in our calculator now. That gets us 1.87 times 10 to the power of negative 9 for our molar solubility S of gallium hydroxide. So we can go ahead and fill that in over here in our answer box. We've got 1.87 times 10 to the power of, remember we write that as E on this platform, negative 9. Now we're told the scientists add some gallium hydroxide to a 0.2 molar solution of calcium hydroxide, CaOH2 at 20 degrees C. We're told to assume that the calcium hydroxide is entirely dissociated into its ions. And we're asked to complete the ice table for this reaction. Okay, so in this question, we're starting with a 0.2 molar solution of calcium hydroxide, CaOH2. So that's what we're starting with. And we're told it completely dissociates into its ions. So we're going to have calcium 2 plus ions and OH minus ions in our solution. Now, since calcium hydroxide has OH2, when that dissolves, we get 1 CO2 plus, we get 2 OH minus. If we had 0.200 molar calcium hydroxide, that's going to give us 0.200 molar calcium ions, but double that of hydroxide ions. We're going to have 0.400 molar hydroxide ions, because for every formula unit of calcium hydroxide that dissolves, we get 2 hydroxide ions formed. So our initial concentration of hydroxide is 0.400. Gallium is the other element in our ice table. Now we're just adding some solid gallium hydroxide. So to start with, we don't have any gallium dissolved, so that's going to be 0. Some of that gallium hydroxide is then going to dissolve, so at equilibrium we'll have some gallium ions and we'll also have hydroxide ions. Our next step is to figure out our change in concentration. Now, we haven't been given the equilibrium concentration for either of our compounds, but to find the change, we can use our chemical equation to write an algebraic expression for the change in each thing. So if gallium hydroxide, which is a solid, dissolves, so we use up X of gallium hydroxide, we're going to produce X of gallium 3 plus ions, and we're going to produce 3X of hydroxide ions because we have a coefficient of 3 there. So our changes are going to be plus X for gallium and plus 3X for hydroxide. So our equilibrium concentrations for gallium is going to be 0 plus X, which is just X, and for hydroxide is going to be 0.4 plus 3X. Now, in this particular situation, we have gallium hydroxide that's going to be dissolving. And looking at our KSP value, it's very small. It's times 10 to the power of negative 34. That's tiny. It's way less than 1. So that means we're only going to be getting a tiny bit of gallium dissolving. So our change in concentration is going to be very small compared with 0.4. So small that doing 0.4 plus 3 times X is going to be basically the same as just saying 0.4. So we can say that this is basically equal to just 0.4. This is called the small x approximation. So we're basically saying x is so small compared with 0.4 that it's basically not there. It doesn't add anything to our number. So we're using the small x approximation to simplify our algebra to say that the equilibrium concentration of hydroxide is going to basically just be 0.4. It's barely going to change. Okay, so our next step is going to be using our equilibrium concentrations in our KSP equation. So we've got KSP is equal to gallium 3 plus concentration multiplied by the concentration of OH minus to the power of 3. So we can put in our values for KSP. We know KSP is 3.31 times 10 to the negative 34. We can put in our gallium 3 plus concentration, it's going to be X, and our OH minus concentration is going to be 0.4. We're approximating 0.4 plus 3x is just 0.4. That's going to be to the power of 3. So to solve this, all we need to do is divide by 0.4 cubed on both sides to get us x is equal to 3.31 times 10 to the negative 34 divided by 0.4 cubed. So if we put that into our calculator, it gets us an answer of 5.17 times 10 to the power of negative 33. Awesome, so we found x, so we can now go ahead and fill out in our table what our changes in concentration will be. So for gallium 3 plus, we have plus x, which is just going to be plus 5.17 times 10 to the power of negative 33. For hydroxide, we have plus 3x, which is going to be plus 3 times 5.17 times 10 to the power of negative 33. When we put that into our calculator, we get positive 1.55 times 10 to the power of negative 32. So that's going to be our change for hydroxide. So let's go ahead and put those numbers into the change in concentration row in our table. And remember, times 10 to the power of is written as E on this platform, negative 33. And for hydroxide, it was 1.55 times 10 to the power of negative 32. Awesome. Okay, so we've got our changes in concentration. Our last step is to calculate our equilibrium concentrations. So for gallium 3 plus, it's going to be 0 plus 5.17 times 10 to the power of negative 33, which is just going to give us 5.17 times 10 to the power of negative 33. For hydroxide, it's going to be 0.4 plus 1.55 times 10 to the power of negative 32. Now we can see here how much smaller the change is compared with the initial concentration. It's 1.55 times 10 to the power of negative 32, whereas 0.4, that's 4 times 10 to the power of negative 1. That means the change in concentration is 31 orders of magnitude smaller than our initial concentration. So it's absolutely tiny. And if you put into your calculator 0.4 plus 1.55 times 10 to the power of negative 32, the answer it's going to give you is just 0.4, because your calculator is saying that number is so much smaller than this, it doesn't affect it. So that's proof to us that our small x approximation worked, because the change we found is so tiny, it really does not affect our concentration of hydroxide. Okay, awesome. So we filled out our ICE table, we found our changes in concentration and our equilibrium concentrations for each of our ions. Next, we're asked what is the molar solubility of gallium hydroxide when it's in a 0.2 molar solution of calcium hydroxide at 20 degrees C. So the molar solubility is the moles that are dissolved per liter, which is the same as the molarity. So we can see here our equilibrium concentration, our molarity, was 5.17 times 10 to the power of negative 33. So that is our molar solubility of gallium hydroxide when it's in this solution. So we can go ahead and fill that in here. It's 5.17 times 10 to the power of negative 33. Our final question asks us, how does the molar solubility of gallium hydroxide affected by the presence of calcium hydroxide solution instead of pure water? So let's compare what we had. We calculated at the beginning the molar solubility in pure water was 1.87 times 10 to the power of negative 9 molar. At the end, we found our molar solubility in our calcium hydroxide solution was 5.17 times 10 to the power of negative 33. So when we have calcium hydroxide solution instead of water, our concentration decreases by a huge amount. We've gone from times 10 to the power of negative 9 to times 10 to the power of negative 33. So we have way less of our gallium hydroxide dissolving than we would have if we were in pure water. So we can answer this last question here. The solubility of gallium hydroxide decreases because we have way less dissolving. So this is a calculation that proves the questions we've already done on the common ion effect. So here we're talking about the solubility of gallium hydroxide in the presence of calcium hydroxide. Hydroxide is our common ion there. So because we have added hydroxide in the products of our equation, our equilibrium is going to shift to the left towards the reactants, which is the solid, decreasing the solubility of our salt. And that's exactly what we found here. The solubility decreased from 1.87 times 10 to the negative 9 molar in pure water to 5.17 times 10 to the negative 33 molar in calcium hydroxide solution. So just to summarize what we did here, we started by finding expressions for our solubility product constant, KSP, in terms of both the concentrations of the ions and the molar solubility of our salt. Then we calculated the molar solubility using the KSP value provided in the question. Next, we started thinking about adding that salt to a solution that contained a common ion. So first we needed to figure out the concentration of the common ion using the concentration of the solution. Then we wrote out an expression for the change in concentration using our chemical equation. The coefficient of each of our products tells us how many X we have added when we change the concentration. We found the equilibrium concentration by adding the initial to the change. One special thing we did here was we used the small x approximation. So if we have a bigger number plus x, and we know x is going to be really tiny, we can just ignore the fact that we're adding x because it's not going to affect our answer. So that's what we used here to get 0.4 for our equilibrium concentration of hydroxide. Next, we substituted in our equilibrium concentration expressions to our KSP equation. And we used that to find our equilibrium concentration of gallium 3+ ions, which is the same as our molar solubility of gallium hydroxide in that solution. Finally, we compared our new molar solubility with the molar solubility in pure water to determine if the molar solubility increased or decreased in the presence of the solution.